first thing that you want to do is you go onto this particular website called Tinkercad, and you log in on that particular website by using your Google ID. So you can click on login here and use your Google IDs to log into the Tinkercad website. Once you have logged in into the Tinkercad website, I've already logged in, so you can see here they are. All right, and just log in with your Google IDs and wait till you get to this particular page. Right here you have this load, and you go here on circuits, click on circuits, click on circuits, click on create a new circuit, click on create a new circuit, and then you get this particular page where on the right side you will have breadboard, you will have a battery. Now I've taken a breadboard and pulled out a breadboard onto my workspace. I have taken a capacitor and pulled it out into my workspace. Right, and now what I can do is I can adjust the value of the capacitor, microfarad, nanofarad, whatever I want, by adjusting these values here. Right, so I want my capacitor to say 0.1 microfarad. I do that here. I'll talk about this working in Android also. Let's take a resistor, put in a resistor, 10 kilo ohms. Okay, and these are annotation tools. Right, I can bring an annotation tool and I can write what this is. Yeah, I can give the annotation tool a name and I could write what this particular thing was. I could say that this is a capacitor of 0.1 microfarad. Right, and I can drag them around. Right, those are draggable. I can adjust the value of my resistor. Right, I can drag my capacitor. Now I've dragged it and placed it on the breadboard. I have taken a resistor, right, and I have, now, all right, it has not been connected properly. So that green color that you see is a wire, right, and it's not being connected properly. Right, you can connect it in that way, but what I'm going to do is I'll delete it in a while. I connect my resistor properly so that it gets connected into the circuit. So I click on the resistor, and then what I do is I have this tool here which is called the rotation tool, which is going to rotate the resistor. Then after a couple of clicks, the resistor has rotated to the angle which I find suitable, and I connect the resistor onto the breadboard. I can also take this and drag it down here, the annotation tool. I can move my breadboard around. Right, I can annotate for the resistor here. Okay. I can annotate the resistor here. So here is the annotated, right, annotation which says that this is a 10 kilo ohm resistor. I have a 10 kilo ohm resistor. Then what I need is, there are a lot of components on the right side. Okay, you can move around. I have clicked here on all components, and yeah, there is a plethora of components available here on the right side. So what I need is, I need a signal generator. Right, since this is going to be a high pass filter, I need something which is going to generate the signal, the sine wave signal for me. So yeah, I have here, that's a power supply. I need a function generator. Yeah, so a signal generator is also called as a function generator. So I drag it and put it. I take one oscilloscope from there and I put it onto my workspace. And then what I'm going to do is I'm going to take the positive of my signal generator or the function generator and connect it to the capacitor, since this is going to be a high pass filter, right? So I'm going to connect it to the, I'm going to take the positive of my oscilloscope, right? I can click, when I click, I can make that turn, and I've connected it to one end of the resistor. Now the other one end of the capacitor. The other end of the capacitor goes to the resistor, and from the resistor, what I've done is I have dragged in one wire here so that I can connect this to ground. All right, so I've connected one wire here, and from here I can connect the wire all the way onto the ground. I have to click here and then turn. I make the click here and then turn and connect it to the ground or the negative of my function generator. Now when I click on the wire, I can change the value, the color of the wire. I can make it black or red as I wish by clicking on it and changing the color here. Is that understood? Right? So now by clicking, you can modify the properties of that particular component. Now I want this to be a sine wave, and you can adjust the frequency, amplitude, DC offset. I'm going to put my DC offset to 0 so that my waveform, sine waveform, will go from minus 2.5 volts to 5 volts. So minus 2.5 to 2.5 volts, so that the peak to peak voltage is 5 volts. All right. So I have made that adjustment. Now I am going to connect the oscilloscope positive, right, to one end of the resistor, and the negative of the oscilloscope would be connected to the other end of the resistor. All right, you click here and then you can drag and change the direction. Okay. So I need it here, so I'll have to click here, click here, click here, and I'll have to click here. So now this is connected. The positive of my oscilloscope, right, is connected to the positive to one end of the resistor. Now what I'm going to do is I'm going to make another connection. This is to the other end of the resistor, and I have now my oscilloscope into the circuit. Now let's say what I've done is I've started the same simulation by clicking here. All right, I see some waveform. Right, I have not adjusted my cutoff frequency. I have not done anything else currently. Right, so I am seeing some kind of waveform here from the sine wave. Right, let me adjust it to seconds. All right, you can adjust this to seconds, microseconds. The time per division that you actually see here. Okay, on the actual CRO, you have a time per division knob, the time sensitivity as you call it. Right, you adjust it with the help of a knob on a CRO. Here you adjust it by adjusting these values here, microsecond, nanosecond, and then adjusting the values here. So you have picosecond, microsecond, nanosecond, and millisecond, seconds, all the way, and right, milliseconds, microseconds, all the way. Right, so you start the simulation here, and now you see that at the output you're going to across the register you are getting a very nice sine wave. Right, now I in a regular lecture, regular practical, in a regular practical you have a dual trace oscilloscope. So two traces appear on the same oscilloscope. There is no such facility here online. So if I want to compare two different waveforms, I will have to connect two different oscilloscopes, which I am going to do here. So I have connected, I have placed another oscilloscope into the circuit, dragged another oscilloscope into the circuit, and then what I have done is I it to I'm going to connect it to the positive of my signal generator. So I will get rid of, yeah, I'll rotate this slightly. Right, so I have enough space here, and that wiring on the board is visible to you. Right, so let me drag it at a place where I find it is comfortable. Right here, if it is comfortable here, then I can rotate it slightly so that the wiring is visible. Once the wiring is visible, I can place it around, and now I have to wire that particular breadboard to this particular oscilloscope. All right, now I have connected. Now let's simulate. I will have to. I can drag around this oscilloscope. Once I wire them, the wires just move along with the oscilloscope. So let's and this button here, when you click it, it centers everything. You can zoom by using the mouse, the middle button on the mouse. Now I see a sine wave on my signal generator onto the right across the resistor, but on my uh, on the resist on the oscilloscope connected to the register, I see a sine wave, but I'm not seeing a sine wave on my oscilloscope, which is connected to the signal generator. And you'll see that the wiring is not done properly. This has to be wired to the capacitor. So if I wire it properly, then and only then will it work. So these are some common mistakes which we make when we do these practicals onto when we perform these practicals onto the bread on a breadboard. Right. So now let's start simulation. Now you can see that I have a nice sine wave for the signal generator, which is visible on this particular oscilloscope, and then I have, which I can adjust. The time per division for this oscilloscope can be adjusted, and here you see the voltages. When I'm expanding, you can see that this entire oscilloscope screen is 10 volts, and you can see that the waveform is taking nearly half of the screen. So it is going from minus 2.5 volts to 2.5 volts. Okay, so you can see that it is going from minus 2.5 volts to 2.5 volts, right? And each division then corresponds to 1 volt. So there are 10 divisions on the y-axis of this oscilloscope, each division corresponding to 1 volt. That is how you can take voltage readings. Okay, and you can increase the frequency here, decrease the frequency here with the help of this knob. Clicking on the knob here, right, you can increase or decrease the frequency. All right, this is on the right that you see is how the simulation would look when you have some 5 hertz applied. Okay, and this is how the simulation would look when you had 80 hertz applied, then 35,000 hertz to 35,000 hertz applied. So I have these applied here. Then, right, I can stop the stimulation. I can change the values to whatever frequency I want, and I can start the simulation again. Now, if you see something like this, on the right hand side across the register, what it means is that the peaks of those waveforms are so close to each other that the signal generator is not able to resolve it. So what you have to do is you will have to change this value, the time per division, to something suitable so that you get a proper waveform onto the screen. Don't think that the circuit is not working. It is actually working, but you're not able to see that waveform because the time per division knob is not been adjusted properly. Alright, you can change the value of the frequency again and run the experiment. Note down the voltage on the signal generator CRO connected to the CRO connected to the signal generator, and note down the voltage on the across the register with the help of the CRO which is connected across the register. You can change the frequency here and note down the voltage. In the high pass filter, what you're going to do is you're going to change the frequency from 1000, 2000, 3000 all the way. We will design this particular filter so that the filter has a cutoff frequency of 3000 hertz, and this is going to be a high pass filter. So all frequencies beyond 3000 are going to be passed, and all frequencies which less than 3000 are going to be blocked by this particular filter. Currently we have not designed it. I am just explaining you how things work on the Tinkercad circuit. Alright, we are halfway through, right? And I have adjusted some 5 kilohertz frequency, and now you can see that how the waveform looks like. Now I can adjust this so that I get a sine wave here. I can adjust the same thing on my oscilloscope which is connected to the signal generator, and you can see how by changing these values I have a slightly stretched out or a slightly compressed kind of waveform appearing onto the oscilloscope. I hope this is clear. Then the next thing that you do is, right, we'll have, all right, I have just adjusted this again. All right, to 5000. I can adjust this. Stop my stimulation. I can adjust it to 1000. I've made it 11,000 as you can see here. And you can do this while the simulation is running, but just give it some time so that after the simulation finishes, you take readings. Like, so you can stop the simulation. You don't have to stop the simulation to take readings. You can just zoom in your mouse button, middle mouse button, zoom in, and then you can pan it by clicking on it and dragging it around, and then you can take readings with it. It does not have those 0.2, 0.4, 0.6, 0.8 mini ticks as you have on the CRO screen, but I think this is fairly good enough for you to take readings. Just use your intuition to find out whether it lies between 2.4 or 2.6. Okay, and yeah, I can change the value here. So nanofarad, I am going to design this for 3000, and I have adjusted the value of the capacitor to be 5 microfarad. So once I do that, and a 10 kilo ohm resistor, my cutoff frequency comes out to be 3000 hertz, right? And you can see here, now I'm going to stop the simulation and run this again, right? That was for 119 kilowatts. Now you see something like this, a band like thing, and your CRO is not able to resolve those peaks because the peaks are very close to each other in time. So you'll have to adjust, click on the CRO and adjust the time per division on each CRO if you want to have a look at those peaks clearly. What I do is this, right? This was 3 hertz. I'll make it 1000 hertz. I'm going to stop, and here you can see the initialization. I have initialized the simulation 1000 hertz. I'm going to zoom in on this particular thing. All right. So the time per division on 100 microseconds. I zoom in. and I can see, you see here in blue you have 10 volts written down, right? And this is 2.5, 2.55, and this is 2 volts. So on the 2 volts thing, you can see that this is 1, 2, 3. So 10 divisions correspond to 2 volts. So each division or each square of this is equal to zero point 0.2, and this is some close to 8 squares. All right. So this is very less voltage. Okay. So when the frequency is less, the voltage is less. As I go on increasing the frequency, the the output voltage is going to go on increasing. For frequency is less than, now this is 2 kilohertz, and you can see that the frequency has increased. Now your scale is 10 divisions correspond to 4 volts. So each division is zero point 0.4 volts, and then you can measure them, measure the amplitude of that particular. Now I make the frequency say 4000, right? And now I should be probably able to see this is also 10 volts, right? So this is 5 volts on the signal generator. Now I zoom in onto the voltage across the register, and this is close to 4. This is close to 4, which is right 2468. This is 8 volts. No, how much is that? Each is 2, yeah. 10 divisions, each is 1, so this is 1, 2, 3, 4 volts. Next thing that you want to do is you simply go on. So my cutoff frequency was from 3000. So what I'm going to do is I'm going to take readings from cutoff frequency divided by 10 to cutoff frequency into 10, which means I'll take readings from 300 to 30,000 hertz, and I'll go in steps of 1000 and very close to my cutoff frequency. So I know my cutoff frequency is say 3000 hertz. Then from somewhere from 1000 hertz to 3000 hertz, I'll take more readings. Say every 100 or every 200 hertz, I'm going to take readings till I reach some 3000 or 4000. After 4000, I can take readings in, I know it's going to be a flat part. So when I reach that particular flat part of the high pass filter, what I'll do is I'm going to click on change the frequency by say 2000 hertz till I get 30,000. So look at this particular thing, 10 volts for this entire white. You can see the mark here, this mark here, right? The marks on on the right. You see 10 volts, and there are 10 vertical divisions. You can see 10 different lines onto the screen, vertical lines as well as horizontal lines. So the 10 horizontal lines, okay, tell you that each of that square is on the y-axis. Each of that square is each of that line corresponds to 1 volt on the y-axis. And you can have a look at the waveform. The waveform looks 1, 2, 3, 4, and point 3 on either sides. So it is going to be exactly 4.6 volts. Now you can argue that it could be 4.5 or 4.4, right? But that's not the point here. That the point here, to understand it, it is increasing. The voltage is increasing as you go on increasing the frequency, and after some time the voltage is going to remain constant. I'm going to zoom out of this, adjust it, adjust this. If I make it slightly 10 milliseconds is what I do, and I stop the simulation right with 10 milliseconds. I make I make the value 100 milliseconds and start the simulation. At 100 milliseconds, I'm not able to see anything. Make it microseconds. Stop simulation, start simulation, and now I have the waveform onto the screen, so I can take readings. Right? This is how that particular circuit will work. I can click on the signal generator, change the frequency. I've made it 12,000 hertz. I start the simulation. I note down the input voltage from this CRO, and I note down the output voltage from the CRO across the resistor. And I stop the simulation. Right? Then I again increase the frequency, and I again note down the readings. And you can see now that if I go on increasing the frequency, the value of the output does not change. This is 5 volts, and this has already reached 5 volts. This is close to 5. So you can see it's 2.5 squares on either sides. And on this particular CRO, yeah, this is 10 volts, and this is also 2.5 on either sides, or it's almost, yeah, 2.5 on either sides almost. So it has reached the flat part, and you can see I can change the value there, time per division, so that I get nice one complete loop here on the CRO, and I can find out the peak to peak values. And then I go on increasing the frequency again, and then noting down. So this is for 25,000 hertz. I start the simulation, and I note down the peak to peak value, and I'll go on like this till I reach a value of 30,000. Since my cutoff frequency is what? My cutoff frequency is 3,000. I started this experiment with 3,000. 3,000. When I took the 5 nanofarad capacitor, I adjusted my cutoff frequency to be 3,000 hertz, 3 kilohertz. Is that clear? Okay. And you can keep on varying this and noting down the voltages uh, on the from the y-axis on the of the CRO. Is that clear? Okay, I can adjust this, and because I had placed a 5 nanofarad, I had changed the values of the capacitor. What I'm going to now do is I'm going to change the annotation here and make it 5 nanofarad capacitor. So here am I am going to make the change. Yeah, this is a 5 nanofarad capacitor. All right, and I hope this should solve my problem. Now what I'm going to do is I'm going to write down the cutoff frequency, and I'm going to write down what this particular thing is, what this particular circuit is. So I'm going to write down that the cutoff frequency for this particular circuit is 3000 hertz, right? And I'm going to give this circuit a name. So I'm going to pick up another annotation tool, and I'm going to write it down. I'm going to give this particular circuit a name. I'm going to call it a high pass filter. Okay, and this ends the video. Right, this video ends along with my explanation for your right. So now I'm going to